So we want to start our lecture for today. And we are looking at some discrete distributions, particular discrete distributions that we are looking. I want to start by looking at hypergeometric distribution. Can you guys hear me?
Yes, please, Doc, we can.
Yes, sir.
Okay. So hypergeometric distribution is a discrete one, which simply means that it deals more with integers, positive integers. And it describes the number of successes in a sample without replacement. The key word is without replacement. Now, sometimes in real life, you apply it in genetics, games, finite population statistics, quality control, even in performance measurement, you apply it there. It's a very useful distribution and it's so easy to use, and you see how it compares with the binomial or negative binomial distributions. Okay, so let's look at a population of size n. Okay, n is the total number of items in that particular population. M is the number of successes. It can be the number of defective items. So out of the n, you can get m. So the number, if m is the defective item, say defective red balls or something, then those that are not defective will be what mathematically? Who can tell us? Those that are not
n.
M minus n. Very good. Okay. So that becomes the number of the failures in this contest. These are the good ones. The good ones. If you're talking about red and black balls, that's it. If you're talking about male and female, n minus 1 is male, m is female. And what is the relationship with them? Okay. So you can see that n minus m equals n. Sorry, n minus m plus m equals n. Okay. We can draw a sample of a particular size, say n, without replacement. And on the basis of that, we can define the random variable. Just like we would have defined a binomial probability distribution random variable. We can define this particular random variable as x, where x represents the number of successes in that particular sample. Okay. So these are just beginning definitions. Now, the possible values of x, just like even in a normal distribution, the possible values of x is going to be a maximum. Okay. So the x is going to range between a maximum and a minimum. And the maximum is n minus n minus m. Okay. Which is a failure. Okay. It ranges between the failure to the actual success. Okay. Where the sample size also ranges from 0 to n. When you have a sample, a range like this, it ensures that you cannot sample more successes than it is. In other words, if you want a success to be x, if your success is x, you cannot get more than m. Okay, remember the way we define the m? The way we define the m is the number of successes. Okay, number of successes. So if what you are looking for is male, it will become the number of successes will become the male. But you are sampling no more than the number of successes that exist, and also no more than the sample size that exists. So your random variable, which could be any possible number, cannot be more than the sample size, and fewer than needed when good items also run out. Now, you remember the formula for combinations and permutations. If you don't remember, I've just put it here. If you are doing a permutation or combination of something, the combination of two numbers where n is the bigger number and R is a smaller number, which is what you are selecting from the N, then the combination is defined as the N factorial divided by R factorial, N minus R factorial. Okay. Please write this formula down. Write the combinations and the permutations formula down. When you are done, just say done.
Done.
Okay. Doc, done.
Done. All right, okay. Lovely. So you have these combinations and permutations. We'll come back to them because most of the things we do are based on combinatorics. Now, the hypergeometric probability mass function is defined as what is on your screen. Just like binomial distribution. I don't know whether we've done that. I think we have done binomial, right?
Yes.
Good. Just
Yes,
like a
Doc.
binomial probability mass function has its own definition, okay, this hypergeometric probability mass function also is defined as x equal to k, where k actually represents that particular random variable in question at the time. And then it's given by mk, n minus k, n minus m, and then small n minus k, all divided by n, m, and n. Now, each one of these things that you are seeing are combinations. Okay, they are combinations. So, for example, mk is actually going to be like this formula here. So, in this case, the m will be the small n, and the k will be the r. So, when you're substituting, wherever you see n for no, you substitute m for mango. And wherever you see k, you substitute. You see R, you substitute K. And so you can use this together with the factorials to actually form your work. Do you get it so far?
Yes, Doc. Yes, Doc.
Okay. I don't know why my microphone. Okay. Sorry. I'm being very careful. Something is still wrong. I don't understand. All right. So you got this formula. So the same way, if I'm calculating the top one and the down one, the same approach. Okay. So m over k, mk is ways to choose k successes from the m, ways to choose the remaining n minus k from n minus m. And then the total possible sample size is what you see here. So that is how you define a hypergeometric PMF. And so we are going to take an example here. Ordinarily, this example is supposed to be. So we're going to take a simple example to work out. So let's assume that you have a population of size 20. It doesn't matter what a population is. It's a population of something, items, goods, human beings, anything. And then the number of successes in that population is 7. The sample size without replacement. So if you sample without replacement is k. That is 5. And then k is the number we want. So let's assume that we want the probability that if you select without replacement, you're going to get the random variable to be equal to 2. Okay. So this is your situation. The first thing we are going to do is to calculate this thing one by one. So I'm going to calculate this first one, and then we calculate this second one, which is the n minus m, and then the nk, and then we calculate the capital N at the denominator. So we calculate each one of them one by one. Will you be able to do the first one, mk? Okay, so mk is, let me start that first one for you. Mk is actually m factorial divided by k factorial. You have the formula there, and then m minus k factorial. Your m is 7, your k is 2. You substitute it, okay? And then here, you can see that I have 7 times 6 over that. Now, another tricky question for you. Why do you think this gave us a value of that? Of course, you can see that when 2 goes into 3, when 2 goes into 3, what do you get?
2 goes into 6, rather.
No, you mean 2 goes into 6.
2 goes into 6, what do you get?
3.
3. And 7 by 3 is 21. Now, why do you think I just wrote this one? 7 times 6 and then 2 times 1. Why did I just write that? Because technically
No.
that is not a factorial.
Because
That's because, okay, it cancels it out with the numerator.
What
The
cancels?
denominator. Look, we have 2 factorial and then 5
Yeah,
factorial.
what cancels? What exactly cancels?
The 5 factorial from the
Exactly.
numerator.
So it's a
cancels
5
that from the-
factorial that cancels. That's the key point. The 5 factorial cancels. You are left with 2 factorial. Okay. And that is it. You are left with the rest of the factorials, which is 7 and 6. Actually 7. Okay. And so it will come with its 7 itself and then 6, and that gives you the 21. Okay. So I want you now to find the n minus m. Okay. This part here. I want you to find the n minus m and then the n minus k and tell me your answer. When you are done, find the n and the n and also tell me your answer. You have the formula. I hope you wrote the hypergeometric formula. Did you write this
Yes,
formula?
Doc.
Okay. So I'm going to use that formula because you will tell me to give you the numbers. So I just want to focus on showing you the numbers. Find that and let me know. So very good. You all did well by calculating the n minus m. You all got 286, which is correct. And then you all got the next one, which is the combinations of 20 and 5. You also got 15,504. That is also perfectly executed. Very good. So in finding, once you got this, you can now put them together. Okay. So if we are to find the probability that x is hypergeometrically distributed and the random variable is 2, then we can substitute that 2 into this. We multiply the 21 by the 286 divided by this, and that will give you approximately 38%. Okay. So you can say that the probability of actually having exactly 2 of that particular item is 38.7%. Any question on that? Let's go to the next. Very good. So Emily, you got that correct. This is not a test, so don't worry. I don't give that easy kind of test.
don't remake.
Any distribution will have its expected value and variance. And therefore, it will have its mean and standard deviation. So if the random variable has a hypergeometric distribution with parameters of n, m, and n, then the mean is given as small n multiplying capital M divided by capital N. The mean is given by that. Please write it down. And the variance is actually the mean multiplying this. Okay. The variance is the mean multiplying that. Now, what is this latter part? This latter part is actually a correction factor, which reduces the variance. In other words, it corrects the variability from preventing it from becoming too wide. Okay. So write these formulae as well. The 16th and the second one Wednesday, October 29th. And our initial task. All right. So let's take a practical example. Jerry, this is where your test comes into the power. I hope you've written the variance formula and all this.
Please, I didn't get the variance. I just came back.
This is now back on your screen.
Thank you very much. Thank you. I have it now.
Are you done?
Yes, Doc, please have it now. Thank you.
Very good. Now let's go to a question. Of course, you can choose to answer this question as a test, or we'll do this one and then the other one you do it as a test. Which one? Emily is very good at prediction, right? She's excellent when it comes to prediction. Oh, don't worry. We are going to do it together. This is not the test that you're going to do. This is a little bit tricky, though. But at some point, I'll let you be doing the computations. So somebody should read the story. Let's see. Albert.
Okay. It says, a geologist has collected 10 specimens of ballistic rock and 10 specimens of granite. The geologist instructs a laboratory assistant to randomly select 15 of the specimens for analysis. A. What makes this hypergeometric? What is the PMF of the number of granite specimens selected for analysis? B. What is the probability that all specimens of one of the two types of rock are selected for analysis? And C. What is the probability that the number of granite specimens selected for analysis is within the one standard deviation of its mean value?
Very good. This is a typical exam question, just so you know. Good. It's not just calculating, but it's also understanding. That's why the first one said, what makes this hypergeometric? What do you think? What really makes this hypergeometric? Okay. Because we explained the hypergeometric distribution. Let me just go back to refresh your mind. Okay, this is where we began from. Hypergeometric distribution is a discrete one. It describes a number of successes in a sample drawn without replacement from a finite population. And then you will have the following. If you check very carefully, we have the number of successes. You see, this thing might look like binomial if you check it carefully, but there's something that makes it not binomial. Who can guess? Who can catch it? There's something that makes it not binomial.
Without replacement.
Good. How is that an issue here? What does without replacement mean?
Binomial goes with replacement and without replacement, but hypergeometric.
Are you sure with that one? Are you very sure? Because now you confuse yourself and confuse us. What is the difference between the hypergeometric and the binomial distribution? You started well. You really started.
No. Hypergeometric concerns itself with.
You said that this one has without replacement. And I thought that they are going to say that the other one, the binomial, is with a replacement, isn't it? But you said the binomial is also without and with. Okay. Or is that not what he said?
Yes, that's what I said.
But it can be. So the binomial, the sampling is done with replacement. Here, the sample is done without replacement. Here, once you you select the particular item, you don't return it. But in the binomial, each sampling is with replacement. That is why we normally say in binomial that each trial is independent, if you can remember. The probability
Yes.
stays the same.
Yes.
The probability in a binomial does not change, but here the probability change after each draw.
Okay.
I'm just giving you the general thing. So the sampling method alone makes it an issue. Also, there's something in here. Is it written there regarding the population? In binomial, the population can be very large. But here, and very large means that it can be infinite, isn't it? In binomial. But here, there's something that tells you that the population is not infinite, it's finite. What do you see there?
No.
It's there, it's written there.
Okay, specify that it's from a finite population.
Exactly. So the second thing is that, I'm just comparing before we come to this particular question. Okay, with binomial, it's with a replacement. With hypergeometric, it's without replacement. With binomial, it is infinite. With hypergeometric, it is finite. What else? We've already spoken about the probability of success. Okay, that in binomial, the probability of success will remain the same. Doesn't matter how many times you trial it. But in hypergeometric, the probability of success can change. Now, keep that in mind and let's go back here. What makes this question hypergeometric? At this stage, you should get it. Did you list all that I said?
Yes, Doc.
Good. So what makes this one?
That is hypergeometric because it has a finite population. Like they collected 10 specimens. Like it's stated there that it's 10.
Okay, but technically,
so
the population, is it 10?
It's 20.
So what is 10 here?
Is it basaltic rock and then the granites that they collected?
No, wait. What is the 10?
Is it the event?
No.
Okay. Not the N.
No, what is the 10? You said the population is 20. Agreed. Okay, so
Yes.
what is the 10? Before you can tell me that a population is 20, finite, then you must tell me what the sample is. So the 10 is what?
No, that's the small N.
Of course, I know it's a small N. I'm saying that the 10 is part of the population, isn't it?
No, it's not
so it's a sample. It's a sample.
The sample.
Okay. If the 20 is a population, the 10 is a sample. Does that make sense, Emily?
Yes, Doc.
Okay. Because we've had two specimens and we've combined them here. Okay. What else?
Doc, please, can I ask you a question?
Yeah.
Please, we said that the hypergeometric, the population is finite, and the binomial is large. But
it's large means it can be infinite.
Okay.
So if the large is confusing you, it's infinite. That's the word. Have you answered? Is your question answered?
Yes.
That's to say you can throw the coin 1,000 times, or you can throw it just 2 times.
Yeah. That's binomial.
Okay. But do you have something like maybe a threshold, like maybe when it is 30?
For which one?
That is very. I'm talking about the binomial. If it's maybe more than 30, that's what you can say is large. Because large looks really.
That will come from the probability of success. That will come from the success you're looking for. Okay. That will not come from the sample. It will come from the success. But then, you see, we are not talking about if you have been given an example. We are talking about even if you don't have an example, once you talk about the toss of a coin, okay? Once you talk about the toss of a coin, let's take, for example, if you toss a coin 10 times and counting the number of heads, You toss a coin 10 times. You count the number of heads. Okay. You can also toss the coin many times. You can. But if you select 5 defective balls from a batch of, a particular number of balls, where let's say you select 5 from 100, okay, and 10 are defective, but you don't replace them. The fact that you don't replace them means that you reduce the sample size each time, isn't it?
Yes, Doc.
Yeah. All right. So let's go to the next one. We spoke about the success.
Okay, Doc, please. So in this case, it's like saying for the hypergeometric, it's possible for the probability of success to be 0 if you go on long enough.
Yeah.
Yeah, false probability that it's not possible.
Yeah.
Okay.
Now, in this very question, what is a success? The success is selecting what? You are successful when you select what?
For the first one, a granite specimen.
Exactly. So the success is selecting a granite specimen. Take note. Okay. And there are how many granites in this population?
10.
10.
Good. So in your letters, capital N is what? Capital M is also what?
So capital N is 20, and then capital M is 10.
Good. Now, when you look at the question very carefully, what is small n here?
Okay, the small n is 15.
What makes you say that?
Okay, so the sample they are randomly selecting is 15.
Yeah. It was so obvious that that is a sample size. That is a small n. Which means that one particular variable we are left to be able to calculate our hypergeometric equation is what? Is the x. I mean, it's just like the same thing with binomial, which we normally tend to say that it comes from the question itself. So when you look at the formula for the binomial hypergeometric, okay, you have all the key things, and that x is in this very formula is a k. Remember, I've said that x is k, so I can make it small x or I can make it small k, but that is a success number that you're looking for. Let's go down. So identify all your elements. Write it down before we go to it. So coming back to the first question, what makes it hypergeometric? You've said it. Okay, you got a final population of 20. Okay, you have success, which in this case is M. You have sample size. Okay, and then we know that the X is going to be the number of granite specimen in the sample. But there's one key thing that even makes it more hypergeometric than anything. There was a word, a phrase, or something.
Look, please, before we come to that, what does the PMF mean?
Probability mass function. Probability mass function.
Okay.
In this question, there is something that gives you the intention that you are sampling without replacement. How do we know that? Because it's something. Of course, it's not written verbatim for you to get it. We are sampling without replacement.
Doc, I think it's the instruction that the person should select 15 samples for analysis. So if you are selecting 15 samples, once you select it for analysis, you can't replace it again because you've already.
That is good, but how do you know you can't replace it again? I like that part. How do you know? That's good. How do you know that you can't replace that thing again?
Because he's already conducted the analysis once he does. So there's no point redoing it.
Yeah, it's because of the word select. I mean, you're right. I mean, coming back to it, it's because of the word select. Because if you look at binomial, we don't do a selection. We rather have the sample. We rather have the sample. We don't sample from the population. Let me check any binomial question we looked at. Okay, we are selecting. So this one carries some sort of normal distribution, but the thing is that in the case of normal distribution too, there is no populative, there's no population. But here you are given a population. Well, you have to find that you are given a population, and then from the population, you do a selection from it. And that is how we know that we are not doing replacement, because when you look at the question, check the question, your question is based on the selected. Do you realize that? What is the probability mass function of the number of granite specimen? We didn't have only granite specimen. We also had what specimen?
Basaltic.
Yeah, we also had basalt. Okay. Another name for basaltic rock is basalt. So we had basalt, and then we had this. Okay, so that is how you are able to attack this very one. Let me just clean it. Then you can analyze all of that. Yeah. So these are the reasons why we know that this thing is hypergeometric than binomial. So when you're given two questions where one is binomial and one is hypergeometric, you should be able to distinguish between the two.
Okay.
In binomial, you are looking for well, let's forget about the x, the particular random variable in question. But you normally have probability of success, probability of failure, isn't it? Or normally you are given one, then you deduce the other from that. So if the probability of success is P, the probability of failure is 1 minus P. You deduce these two from the question. And then you also have a sample size, not a sample size selected from a population. So by having that sort of sample size, the population becomes infinite. That's what we're saying. Because you don't have a finite population provided. Okay, let's go to the next one. So now we come to what is the probability mass function of the number of granite specimens selected? Now, we are looking for the probability mass function. Let's just recap ourselves some few things. We know that the hypergeometric probability function, we know, you remember that it was mk, do you remember that one? And in this question, what is our m? Let me just show you here.
M is 10.
Okay. So this is a hypergeometric probability mass function. So what will be the m here? 10. What will be the n for no?
Dot 10.
20.
Okay. And what will be the small n here?
15.
15. What we don't know, we've not been given, is the k. So at least we know these elements. That's why we are being asked of the probability mass function, because the mass function will mean that k or x here must be of multiple different values. Okay. So you substitute that to find the probability mass function. So you have this hypergeometric probability mass function like this. You substitute everything, but here is the thing. We know that we don't have the k yet, but we know that k also satisfies combinatorics constraints. What does that mean? Because whenever you are calculating the 10 and the k or x, you calculate them using combinations. You remember?
Yes.
We calculate them using combinations. And you remember that there was a potential maximum value that we gave. Let me just recapitulate your mind a bit. Okay, the hypergeometric, the probability mass function. This was the possible values that the random variable can take. So if you substitute n is what?
15.
No, the big
So
thing
what
is
to be
20.
the left side here? What to be the left side? It will be 0 and what?
0 to be
Capital N is what?
20.
20.
So 20 minus 10 is 10, and small n is 15. So 15 minus 10. So 0 and 5.
Good. You got 0 and 5. What else? So the left side is 0 and 5, but that becomes we are taking the maximum. Okay.
Yes.
And then you now have your X. What will be the minimum NM?
15 and 10.
Say it again.
15 and 10.
Exactly. 15 and 10. So the K, which in this case is X. In fact, if you want, you can just say this X is also K. So the K, which is the X, will fall between some values. What to be the value that it will fall between? On the left side, we are going to have 0M, but you take the maximum value. On the right side, it's going to be between what and what?
15 and 10.
You take the minimum value. Yes.
So 10 and 5.
So what would that be?
Between 5 and 10.
Yeah.
So X is between 5 and 10.
It's between 5 and 10. That is a value you get. Okay. And that is what you're going to use. So all the possible values of X are going to be between 5 and 10, between 5 and 10, each one of them. And that is it. Right. So now we're going back here. We don't know yet because we were told to give the probability mass function. Emily, you were asking, what is a PMF? You were told to find the probability mass function. So the probability mass function is going to be possible values of X or K. Okay. So when you find this and you take this range here, you're going to get that possible values of that, and it's going to be between 5 and 10. Remember, they have to be discrete and therefore positive whole numbers. Albert, does that make sense?
Yes, Doc.
Now, if you follow the pattern for these values, you can calculate for each one of them. If you substitute the value for K or the value for X, you can find the probability that this thing is equal to 5, equal to 6, equal to 7, equal to 8. You know that?
Yes.
Okay.
Yes.
So, yeah, if you have to do for 5, you get something like this. But you can do for all of them. So you can do when it is equal to 5, when it's equal to 6, when it's equal to 7, when it's equal to 8, when it's equal to 9, when it's equal to 10. You can do for each one of them. And then you will have the probability of each of the X or each of the K. But of course, that function is not what you are supposed to calculate. You are supposed to give the value is not what you're supposed to. You're supposed to just give the function. That's it. You're supposed. So if you remember the question says find the probability mass function. Where is that? It says that what is the probability mass function of the number of granite specimens selected? But you can't find also each one of them. Okay. Because I can now ask you what is the probability that that selection, the probability of success is actually equal to 5 or equal to 7 or equal to 10. You cannot. Okay. The next part of the question is this. What is the probability that all specimens of one of the two types of rocks are selected? This is interesting. All specimens of one of the two types of rock are selected. How will you go about that? All specimens. So I've written it here. The probability that all specimens of one of the two types are selected. What is the probability? Well, the first thing we need to understand is all of one type means what? All of one type, all specimens of one type means that it is either going to...
It means that all 10 are selected.
All 10 of what? You have got to be specific here.
All 10 of the, let's say, granite rocks are selected.
Good. So that means that X will be 10. Or what?
Yes. Or 5, because we are looking for 15.
No, wait. It says all of one type. So one type is what you've just spoken about. You've spoken about granite. So
Yes.
you see that all 10 of the granites are selected, which means X is 10, or all of what are selected.
All of the basalt, yeah.
Yeah, the basaltic rock. Okay, so is either one of them. That is all. Now, let me ask you, if all of the basalt are selected, okay, let's just say here that X is 10 for the granite, okay, and if all of the basalt are also selected, you also have 10. Now, if all of the basalts are actually selected, the sample is 15, isn't it? According to the story, the sample of 15 contains 10 of the basalts.
Okay.
So if all of the basalts are actually selected, then it means that the sample of the 15 will contain 10 of the basalts plus 5 of the granites. Do you agree with that?
Yes.
So in this case, if all of the basalts are collected, then we have 10 straight away. Sorry, all of the granites are selected. We have 10 straight away. But if all of the basalts are collected, then we are going to have, because we have 15, because the sample is 15, then it means that we're going to have 10 basalts and then 5 granite. So it means that in this case, X will no longer be 10, but will be what? 5. If all of the basalts are collected from the 15. If all of the basalts are collected from the 15, then the only thing left out of that 10 is going to be what? Granite. And therefore, the X, our granite, is going to be 5. In other words, the two events are mutually exclusive. That's what it means. Because once you are at 15 sample size, and they are all supposed to be 10. Okay. Once one is 10, the other is 5, isn't it?
Yes.
Once the other is 5, the other is 10.
Yes.
The two are mutually exclusive. So this whole question, which is asking you that the probability that all specimens of one of the two types are collected, you are looking at the probability of all one type. In other words, you're looking at the probability of all of one type. Okay, and now we know that if we're looking at the probability of all of one type, then we are looking at the possibility of these things up here. Okay, because we are dealing with granite here. So we're going to have the probability that X is equal to 10 for granite. That is if all of the granites are selected. And remember, we are focusing on granite because the others, it's implicit. We calculate the probability that X is equal to 10. Then we add the probability that X is equal to 5, provided that the basalt is 10. So what you are seeing here is for granite. So if all of granite are selected, we have 10. We finished. Granite is actually 10. If all of basalt are selected, what is left is granite. So granite is 5. And that is the all of one type. You see, one type. Don't forget, one type. One type means if I'm taking granite, I deal with granite alone. If I'm taking basalt, I deal with basalt alone. So now you're going to find this probability. The probability that X is what? X is 10. Then you also find the probability that X is 5. Then you add the 2. So you go and take the hypergeometric formula. Find the probability that X is 10 now. Remember the formula? Now we know that in that formula, we know what will fail. Are you with me? So let's go back to the formula. Thank you for writing the formula. So in this formula here, we know that X is going to be 10. And then we also know that X is going to be 5. You add them. Yes, Jerry.
Doc, please, I want to understand the plus. Is it likely to where you would have said that in selecting all of one type, either we are selecting all granite or all basalt. So that plus is deduced from the or. So either we are doing this or at the time
It's
or
simple. The plus is deduced from the or, yes. Because the first one is all of granite selected. The second is all of basalt selected, but because your focus is one type, okay, it's like saying that all of granite is selected. Okay, what is going to be granite? Then all of basalt selected, what is going to be for granite as well? Because the two are mutually exclusive, right? So if I say that, it's like saying that he's a man. Then you come to, I want which of you is a man here? The man will come. Okay. Then I say, I want which of you is not a woman. The same man will come, isn't it? So that is one type. So if all of granite are selected, it means that we are looking for the probability that X is 10. But if all of basalt are selected and basalt are 10, then if the 10 is selected, then the granite, because I've already gotten the first of the either to be 10 for granite. So the next for it will be the rest that will be left. So the rest that will be left will be when all of basalt is selected, then what will be the granite? If the sample is 15 and 10 of them are basalt, then granite will be what? Will be 15. But of course, if you want to turn it way for the basalt, you can do it all for the basalt. So, for example, you can say that if all of the what do you call it? If all of the granite or if all of the basalt is selected, okay, what would be that? If your focus is on the, but remember the focus is on the success, and the success was not what? Basalt. Did you realize that in the question? You go back to the question. The success was about what? Granite. Check it. So we have 10 collected specimens of basalt and 10 granite. The geologist instructed lab technicians to select 15% from the analysis. Okay. Now here's a point. What is the probability mass function of the number of granite? You get a point? So at this stage, the focus is on the number of granite specimens. Okay. So you put basalt aside. We are dealing with, granite. That is why we have the probability of X equals to 10 if all, because you are dealing with all, because you are looking for probability mass, the mass function. Okay. The probability that X is equal to 10 for the granite because there are 10 of the granite. Then if all of the basalt is selected, the probability that the rest will be granite will also be the probability that X is 5. Okay. So that's what you calculate. So when you do the first one for the 10, what do you get? You can do it. I mean, in order for us not to delay too much, I know you can do it. Or you can't.
Yes, Doc. That is 0.016.
Yep. Okay. So for the granite, I mean, this is explanation. So you do for the probability of X equals to 10, you get 0.0163. And then the other one too, you get the same thing, interestingly. If you substitute them, I don't want to be calculated because now you know how to do hypergeometric calculations. And so you add the two, and then you get what? 32.6. What does that mean? Sorry, 3.26. Okay. So what it means is that about 3.26 or 3.25%, there is a hypergeometric chance that all of granite being selected is just 3.25%. That's it. It's just like saying that what is a chance that if I pick for a random, I'm going to get exactly something for binomial or Poisson or anything. That's it. Now, the next part of the question is, let me just go down here. Find the probability that X is within 1 standard deviation of the mean. That was the question. The probability that X is within 1 standard deviation of the mean. Do you remember the mean and then the variance for a hypergeometric function?
Yes, Doc.
Okay, that's the first thing you got to calculate, because you are talking about 1 standard deviation of the mean. So you need to calculate the mean, calculate the variance, and find the square root of the variance, and that gives you the standard deviation. Okay, let's find that. But do you understand what I mean by, if you were to calculate, what is the formula for the mean?
That is n times m over n. That's small n.
Yeah. Okay, good. So you find this small n and then m over n. Is that what you said?
Yes, Doc.
Good. So these are the means and the standard deviation. When you substitute them, you're going to get, because remember, n is 20, m is 10, and then small n is 15. We substitute that, the expected value or the mean is going to be 7.5. The variance is just taking that 20 here, and check carefully the variance. The variance is split into 5 parts. It is this n here, this m over n here, this n minus m over n here, this n minus n over n minus 1. So 4 parts. So you substitute all of that here, and that is going to give you 0.9868. Okay, so that's your variance, but you want the standard deviation.
The formula will be given to us.
Oh, yeah. You have multiple formulae actually. So you now find that variable, you find the standard deviation by finding the square root of the variance, and that gives you 0.9934. Okay, but that doesn't answer the question, because the question says what? The question says, what is the probability that the number, what was the question? Yeah. What is the probability that the number of granite specimens selected for the analysis is within 1 standard deviation of the mean? Now, when you say something is within 1 standard deviation of the mean, how do you find? It's like, if I want to find, the mean is actually represented by mu, isn't it? Okay, so if it is within 1 standard deviation, I need to do plus or minus sigma to know, to find the plus and find the minus, so that you will know how many standard deviation this is. Okay, what is within 1 standard deviation of the mean? So this x, okay, how far is it within 1 standard deviation of the mean? So substitute the value. What is the mean? What is the mean that we found? The expected value.
7.5.
Good. So you do 7.5 plus or minus 0.9934. So you get a lower bound to be 6, because you're subtracting, right?
Yes.
6 point something, 0.5 something. And then the upper bound, you add. So you're going to get 8 point something. But you get it. Okay. So let's do that.
Yes.
So you get 6 plus this, you get 6.4, and then 6.5 something.
6.5066.
Yeah. And then 8.4934. That will give you that. Now, we don't want these 6 decimals, because this is a hypergeometric function. It requires your answer to be integers. So what are the only integer values between this? The only integer values between this are 7 and 8. You realize that?
Yes.
Yeah. So it means that our k or our x, because the question is asking you to find what the probability that the number of the granite specimens selected for the analysis is within 1 standard deviation of the mean. Okay. So you are now going to find the probability of 7 all the way to 8. You're going to find the probability of 7, find the probability of 8, and then add them together. Okay. So let's find that. Because you are looking for the x value. What do you get? You find the probability of 7, you add it to the probability of, again, using the hypergeometric functions, and you can calculate. I mean, at this stage, you have all abreast with that. Okay.
That 7 is 0.348.
Hey, you did that quickly like that.
I'm using the calculator. So I just
I
put
know you're
in
using the calculator, but to do that quickly, that's smart. Yeah, 0.348 thereabout. And then when you do for the 8, Jerry, are you there? You get the same thing.
So I'm here. I'm trying to connect mine. It's not.
Anyway, when you do that, when you do the 8, you will also get the same thing of that. And the reason why you get the same thing is not because it's the same numbers. It's because you are using a different two numbers and they all correspond to the first one. That's why. And if you substitute, you see. So now you add a 2 and you get 69.66%. That's it. So clearly, the chances that a number of granite specimen is selected for the analysis, the chances that this is within one standard deviation of the mean, the chances are almost 70% chance. That's it. Don't forget that this value, if you can remember, the K itself was between 5 and 10. Do you remember? So we are trying to say that the chances that this K is between 7 and 8. Basically, that's what it's saying. The chance, because 7 and 8 kind of matches the mean. The chances that is between 7 and 8 is almost 70% chance, which is true, because we are talking about below the 7, you have 5 and 6. And then above the 8, you have 9 and 10. So clearly, the chances are quite high. That is hypergeometric distribution. Congratulations for understanding it. Any question before we go to the next one?
No, we need more exam type questions to solve on our own.
Yeah, you get plenty. You get plenty, more than plenty. I'll give you plenty to do. And then we'll get similar one also for the exams. But you got to also understand that while I'll give you that, sometimes some of the knowledge you would have acquired here will require you to make some proofs and things. And I've told you multiple times before, nothing will come away from the notes. So you got to also understand the notes. All right, let's move on. Geometric distribution, that's the next one. Geometric. It describes a number of Bernoulli trials performed until, here's the key word, until the first success occurs. In a sequence where each trial is independent. That's one. Each trial is independent. Okay. Each trial is independent, and each trial also has two outcomes, success or failure. Success is P, failure is Q, which is a 1 minus P. Therefore, P plus Q is what?
It's 1.
Okay. Now, each trial is identical in probability across trials. And when you're performing the trials,
the introductory part.
Each of the trials, X is the number of trials up to and including the first success. Okay. And you see this clearly. So if you have X to be 1, it means success on the first trial. If X is 2, it means success on the second trial, but failure on the first trial. If X is 3, it means success on the third trial, but failure on the first and failure on the second trial. Does that make sense?
Yeah, so you stop when you succeed.
That's the point. So you're describing the whole thing. The whole thing is like a Bernoulli trial. But until you get a fair success, you have not actually gotten your probability of success. And of course, you must follow that sequence. So when you have this, then we can say that the random variable, which is 1, of course, is discrete, 2, and also 4. In that case, we can say that this random variable is geometric. Not hypergeometrical, it's geometric. Okay, it's geometric. Now, so how do you write the probability mass function? Remember, all of them, you need to know the formula or the probability mass function, as well as the mean, the variance, and even sometimes the mode. This time I brought the mode. So we need to just know the center as well as the deviation from the center. The center is mean, median, mode. The deviation from the center is the standard deviation and variance. So if you want to get a particular x or a particular random variable, then the first k minus 1 trials must be failures. Okay, the first k minus 1 trials must be failures. So if I'm dealing with 2, then the first one, which is 2 minus 1, must be failure. And then the kth trial must be the success. And so how do you write the probability mass function? It is giving us P into bracket X equals to small x or K, which is equal to the Q raised to the power K minus 1 or X minus 1, and then P, okay. I want to be sure that I didn't write in. Yeah. Yeah, that's it. The Q, where is it? The Q raised to the power K minus 1 multiplied by P. That's it. And K is 1, 2, 3, is a positive, integer. And then also the Q is 1 minus P. Okay. So if you can remember, for example, binomial, we talk about P, and then we talk about 1 minus P. Here we are speaking more of the 1 minus P first before the P. Okay. And for binomial, it was raised to the power n minus x and things like that. But here the P is raised to no power. It's just raised to 1. Now, how do you find the mean? From this thing, you can find the mean to be equal to 1 over P. Okay. And then the variance will simply be 1 minus P over P squared. The mode is 1. So you will never be asked to find the mode because it's already 1. Okay. Of course, P is greater than Q times P. And that is also greater than Q squared times P, and on and on and on. Maybe an example would do, but the question also would be, how do you find whether it is geometric? So here, let's look at it together. Assume that 13% of the people are left-handed. People where? Doesn't matter. 13% of the people in your class are left-handed. What makes this geometric? That's the first one. If we select 5 people one by one at random, find the probability of first lefty is the 5th person chosen. That there are some lefties among the 5. Emily will say that we should give more questions like this so that you understand the thing. Because for the first time, she may not understand the thing. We should give. Okay. How do you go about this? Well, the first thing you got to note is, why is it geometric? So that's the first thing. Let's try and understand that. The analysis we are doing, because remember, 13% of the people are left-handed. Each person is left-handed. That is what it means. And the percentage of people that are left-handed are 13%, which means that the P is 13%, which means that those that are right-handed are what?
About 87%.
87%. Now, watch the next sentence. we are going to stop when we see the first success. We know this.
Yes.
And that first success is a first person who is lefty. Because the question even was, if we select 5 people one by one, we are interested in the lefty, the first lefty. So the geometric distribution model here, is modeling the trial count of the first success, not of success, but the first success. And that requires the trials to be independent with a constant probability of 13%. And this is what we have in our situation. That's exactly why it is geometric. Now, you got to fully understand that this is not the same as hypergeometry, because hypergeometry, we are dealing with replacement. Sorry, we are dealing with without replacement. Is it replacement or right?
Doc, without replacement.
Without replacement.
Yes.
And nothing of that is addressed here. Okay. Next one. Find the probability of first lefty. You see, that first lefty is even a clue for the first part of the question. Find the probability that first lefty is a fit person. The first lefty is a fit person. Now, let's try and get something right. But this is very simple if you know it. Let's assume that the number of people checked till you got the first person is X. So you checked a number of people without, until you got a first person. And Y becomes the number of the lefties among the 5. Because remember, there were 5 of them. Okay. We select 5. So 5 here represents what? K. So K is equal to 5, basically. Okay. Now, if we are going to write the geometric function, so first let's document the geometric function. This is it. Look at it. The geometric distribution, the probability mass of the geometric distribution is given by X being K, 1 minus P raised to the power K minus 1, and then P. Please remember, I'll be using sometimes K minus 1, sometimes X minus 1. Let me see whether I use X minus 1. Okay, I maintain the K. So this is it. So the question now becomes, what is our X we are looking for? What is our P? First of all, what is our 1 minus P? This one you all know. Geometric function is easy. What is our P?
No, P will be 0.13.
And then 1 minus
Sorry,
P.
the 1 minus P will be 0.13. Oh, it's confusing.
No, what you said now is correct. Okay. Remember, P is a probability of success. Q or 1 minus P.
Yes. So Doc, now the probability of success is the person being left-handed. No,
go to the question. Okay. It says, I assume 13% of the people are left-handed. So that is, we already said it here. That is P. Yeah. P is 13%.
Okay.
And 1 minus P, you said it earlier, that is 87%. What I'm simply saying is that is the formula that brings the 1 minus P first.
Okay.
But if you like, you can also bring the P first so that you're not confused, so that you write it that P is equal to X equals to K equals to P, then into bracket 1 minus P, K minus 1. Maybe this one would not make it a bit confusing to you.
That's what we are used to.
I know. But life is not a straight line.
Okay, so that it will be 0.13 into bracket 0.87 raised to the power 5 minus 1.
Correct. 5 minus 1. And then the rest is just calculating, isn't it? You take your calculator. What would that be?
Yes.
If you do that well, you're going to get, the rest is calculator, so no problem. You're going to get 7.45. That was what the question is asking. Lefty. Lefty. Let's just go back and then you see. It says that find the probability that the first lefty is the fifth person chosen. The first lefty is the fifth person chosen. Now we are looking always for the first lefty. First lefty. Probability of success. Okay, it's a fifth person. It's not a sixth person. It's not a third person. It's a fifth person. Fifth person. So K is 5. Okay. And so when you work it out, you're going to get the chances are very slim, as you can see, 7.5 approximately. What is the probability that there are some lefties among the 5? This is a beautiful question. There are some lefties among the 5. Some lefties among the 5. What does that mean?
Doc, I think this was part of the assignment. If they're asking some, that means 1 and above. So you do 1 minus probability that there are no lefties.
Yeah, you got it. Hey, there is. Are you here?
Yeah, we are here.
You don't understand Yaks. Okay.
Yes.
So 1 minus the probability that there are no lefties. That's it. Okay. So first thing, we are looking at probability that some lefties among the 5 people, which means that we are looking for the probability of at least 1 lefty in the 5. So it means that if you are looking at at least one of them is going to be lefty among the 5 there, then it is 1 minus the probability that no lefty, isn't it?
Yes.
So we are taking the opposite, like we always do in normal binomial. So 1 minus the probability that no lefty. So you now find that. You just put that value, none. None means that you're going to calculate P of what? 0.
Yes.
And then you subtract the answer from 1. So this alone, this small one here is a P of 0. Because any number raised to the power 0 is what?
It's 1.
It's 1. Ah, wait. Have I missed something?
It will be 5 minus 1, which is 4. But because it's 0, you have 1, which is the same as.
Which is what? The way it started well, then now you got stuck. Okay, but that is because I am not using, I'm using 13% here. Okay, watch here. It's 13%. So it's 1 minus 13%. Remember that we are looking at the probability that, okay, let's see. Probability that at least 1. At least 1 means what?
1 or more.
Emily, what did you say yourself? But because I showed you the thing, you're also confused.
At least 1 means 1 or more. From 1.
Yeah, but it says that some lefties among the 5. Some lefties among the 5.
I think we are equating the sum to at least 1 because we don't know the number. I don't know if that is.
Which sum?
Some lefties. At least one lefty in the people. That's what we are calling at least 1. So it could be 1 or more.
Yeah, I know it's more. Okay, I know it's going to be 1 or more. So if it is going to be 1 or more, then you can take the knowledge of the fact that probability is equal to 1 and then do 1 minus, opposite of 1 or more is 1 minus none. 1 minus the probability of none.
Yeah. Okay, so Doc, if we are doing the P of 0, that will mean we are going to have the 1 minus the 13. So 1 minus 0.13
You mean 1 minus
to the power
0.13?
Yeah. Yes. Doc, the raised to the power is where I'm having an issue. If I make the K to be 0, we are going to have raised to the power -1.
Yeah, but why will you raise K to the 0?
Okay, K is still 5. So I'm confused as where the 0 comes in, since there's no X here.
Yeah, but it says that the probability of at least one lefty in 5 people.
Yes.
One lefty in 5 people. I mean, myself, I'm just trying to diagnose.
Okay, so Doc, it will be a combination.
Yeah.
So 0, 5. Okay. I now get it.
It'll be a combination. So 0, 5. And therefore, when you take that 0, 5, and you are going to get 49.84%. And when you subtract that from 1, that gives you almost 50%, which is what we have here. All right. The next one is this trial. I can't believe that I'm not letting you do any of them. But anyway, a production, let me do this. A production line produces defective items with probability of 5%. Find the probability that the first defective is on the 8th item. Now, if you check carefully, it's sort of taking more of positioning. That the first defective is on the 8th, so that gives you the geometric, angle, because it's not the probability of success, it's the probability of first success. The second is find the probability that the first defective is after 20th item, and then also find the standard deviation. So let's take the first one. I mean, this one is very easy. The probability that the first defective is on 8. So that means that X is what? S is equal to 8, isn't it?
Yes, sir.
So we are finding the probability. We are finding the probability that X is 8, which is actually equal to 1 minus P raised to the power. So I can just, instead of 1 minus P raised to the power 1, I can just say Q raised to the power. It will be K minus 1, but this one it will be what? K minus 1 is 8 minus 1, which is 7. Then you now have P raised to the power what? No, P raised to the power nothing. P raised to, power nothing. So it's just P. Okay. So you substitute the value for this. Let's find the probability P. P is 0.05. It's up here. 0.05 to the power 7. Multiply by 1. That's it. Do you guys get it?
Yes.
This one is very simple. What do you get? Let me see. If you calculate it, you're going to get
0.034.
Very good.
I think P is raised to the power 1, because the previous question that we did, if you make P to be just
but it's raised to the power 1. We all know any number standing alone is raised to the power 1.
Yeah, so Doc, when we are checking for the P is equal to 0, I think it's going to be raised to the power 0.
Which one?
The P, in this case. So the previous question that we were looking at, please, if you could go back.
Okay. The one before.
Yes, the example 1.
Yeah.
Yes, I think they made the P to be raised to the power 0, since there was no probability of success.
Yes, but when you raise P to the power 0, then Q is raised to the power 5.
Yes.
Yeah.
Okay.
Yeah, we got that one. All right, so you get this one. The second one says probability that the defective is after 20 items. Okay. So after 20 items, that means that X is what? After 20 items. We are looking at probability that X is what? What 20?
21.
No.
X goes 20.
20.
Okay. Yeah.
Remember, the defective is a success. Okay.
Yes.
And
so the X is greater than
20
20.
Exactly, it's greater than 20 because there are so many possibilities.
Yes.
There are so many, items that are after 20. So you just want to find this one, which is not simple. It means that infinity is even a possibility, but we are just looking at the probability.
Yes.
So how do you find it? It means that P is going to be what? First of all, 1 minus P. Remember, P is 0.05, right?
Yes.
So if P is 0.05, 1 minus P is going to be 95.95.
Yes.
Right? So you're going to have 0.95 raised to the power 20. Hey, no. Raised to the power, just like the previous one. Raised to the power 20. Why? Because we are looking at the probability of the first defective. So whatever it is before the first defective is having the power of 0. It's irrelevant. It's irrelevant. So that whole idea of, we used to have K minus what? It was K minus 1. So it means that we wouldn't need the minus 1. And why wouldn't you need the minus 1? Because now we are going beyond. So they are all possible possibilities. I mean, let's just go back here. Let's just go back to the previous one. Okay, here. Because that word, at least one lefty in 5 people, it means that they are all possible possibilities. So there is no need to deduct 1 from the sample that you have, from the sample of question that you have. And therefore, anything about P is 0 in principle, because the 1 is gone. Therefore, the P is which is, when it's standing on its own, is raised to the power 1. The P itself is raised to the power 0 now. So 1 is more or less 0. That's what it means. 1 is 0. So K minus 1 will be K minus 0. And therefore, P raised to the power 1 will be P raised to the power 0.
0, yeah.
And that is it. Exactly the same thing here, because now when you have greater than that, you are now moving towards, there's nothing below 20. That's what it means. There's nothing below
so
20.
it's like simply having Q raised to the power K.
That's the point.
Yeah.
Because you're looking for the first effective, and it starts from there. But this time it starts from there and beyond, from the 20 and beyond. So when you substitute that, you're going to just have K raised to the power 20, or 0.95 raised to the power 20. And that will give you 35.85. As for the standard deviation, we know the formula easily. The standard deviation is given as what? Just let me remind you, go back here, find the
1 minus P over P squared.
Very good. But that is a variance.
Okay, so root of 1
exactly.
minus P.
So you take the root. So you take the root of this, 1 minus P over P squared. Okay. And then you can now substitute the 0.95 you had. And then you can get 19.49. So what is the mean? I mean, we didn't find it. We haven't found it. But you can find the mean.
The mean is 1 over 0.05.
Yeah. So what would that be? I want to use that to tell you something. What would that be?
Doc, 20.
So you see that the mean and the standard deviation are similar.
Okay.
When the mean and the standard deviation are similar, what does that mean?
It means there's no difference between the values.
When the mean and the standard deviation are similar, what does that mean?
There's no dispersion.
Yeah. But what does that mean also? It means there's no, hey, did you say there's no dispersion? There's no dispersion, or there's large dispersion.
Okay, when it's smaller than the mean, there's no dispersion.
Well, the thing is that it depends on what distribution you are dealing with. Okay. Because normally we speak in terms of the fact that we have normal distribution, but technically, if the data set or the distribution has any mean, because that means that they're almost equal. Do you know that?
Yes.
It means they are equal. So it means that the deviation or the spread relative to the mean is almost the same. It means the data is highly variable. That's what it means.
No, please come again.
Okay. It means that the variability is about the same size as the average.
Okay.
The dispersion is about the same size as the average. The values are spread out from the average. And I still am a camera from Mgt Sc. High variability of the data set. How do you understand? Remember that when the mean is, when the standard deviation is way larger than the mean, then there's a lot of variability, right?
Yes.
Yes.
When the standard deviation is zero, what does it mean? When the standard deviation is zero, it simply means that the variables are the same values. So if one is 10, the other is 10, the other is 10, the other is 10. If the standard deviation is zero, it means there is no deviation from the mean. And for you to have no deviation at all from the mean, it means all of them are what? The same.
Yes.
Yes, Doc.
You guys need food. Food, not just food, but even proper food. Okay. So that's it. Let's go to some of the advantages or practical use of this geometric distribution. Practically, where do we use them? So when you are doing a Bernoulli trial, you use geometric distribution when you are repeating identical Bernoulli trials. When you want the first success time, when the trials are independent and the probability of success is constant. But applications are engineering, email spam detection, you can use that. Clinical trials, gambling, telecom, quality control, all of these are where you can apply such geometric distribution. We're going to go to the last one for today. Negative binomial distribution. What do you think that one is going to be? You haven't done any test, eh? Or today we shouldn't do a test.
No, we're going to do the Boisson.
You want the test on the person?
No. You asked what is this one going to be? I said maybe it's going to be like Boisson.
Oh, the negative binomial distribution. It's a generalization of the geometric one we just did. Okay, so it's very similar to binomial, as you can see, except that the number of trials is not fixed in advance. Because when you look at the geometric distribution, the number of trials are fixed. But here, the number of trials are not fixed. Hold on, I don't know whether these people, I can't hear them. All right, so in a negative binomial distribution, the experiment consists of a sequence of Bernoulli trials, because it's come from binomial. Each trial is success or failure. The probability of success is P, probability of failure is Q. When you combine the two, you get 1. The experiment is continued. Here's the point. The experiment is continued until our successes are obtained. So it's just like the geometric one, okay? But the geometric one, the case is where R is 1. But here it generalizes R to multiple ones until the R successes are obtained, not just 1 is obtained, but R successes. You remember that one? It deals with first success. Do you remember?
Yes, sir.
But here it is not dealing with first success. It's dealing with, it can go to multiple. Okay. Let's take an example, an experiment of repeated independent trials. Okay. Each trial produces a success S with a probability of P, a failure F with a probability of K. We know this thing. Then the distribution of this random variable, which is the number of failures, watch the word, number of failures preceding the R success. So you are looking at the number of failures before the R success. This is called a negative binomial distribution. Now, what do you think the number of success after the R success will be what? It's that sort of positive binomial distribution. Do you get it? So the negative binomial distribution is focusing on the number of failures before the first success. Remember the first one we looked at? We were just forgetting the failures until the first success.
Okay.
But here, we are looking at the failures before the first success. That's why we say that it generalizes the geometric distribution. So the probability mass function is given by probability of x. So here I've removed the k, representing it. Is x plus r minus 1, and then r minus 1, okay, where p raised to the power r, q raised to the power x. So the question now some people ask is, why the word negative binomial? Because what you're doing is that you're expanding the binomial series. And this is a binomial series, 1 minus q. Remember, 1 minus q is actually p. Okay, so it's like 1 minus q raised to the power negative 3. You are expanding this, which will produce the following coefficient. Okay, r plus k minus 1, or k. And this one appear in the probability mass function. And that is why the name is negative. Now, in the one I just gave you here, just look at the 1k. Okay, you don't have the k appearing. Okay, but you will have it appear in a different form that I will show you. But the key point is that you have a negative value in there. And the idea is that if you expand a negative value consistently, okay, what it means is that, I mean, if you're on the number line and you keep going left, okay, you are expanding more. I mean, just take the failure. We said that the probability for the first success for the geometry, okay, the more you want to find first success, but you're not getting it, what are you doing to the failure? The more you want to find more success, but you're not getting the success, what are you doing to the failure?
You're increasing the failure rate.
You're increasing the failure, so you are becoming more negative. That's the point. You're increasing the failure, you're increasing more, you're deepening the negativity. And that is why we say there is a negative binomial distribution. So the distribution is becoming more negative. All right. So again, the properties require you to find the mean, the variance, and the mode. Now, remember we said that the mode for the geometric one is what? 1, if you can remember.
Yes.
And this generalizes it. Okay. Remember that the geometric one is where r equals to 1. Success is just 1. Because we're talking about only the first success. Here, success is multiple. And so the mode becomes a little bit, stretching like this. If the success is not 1, but it's this. But if success is 1, then the mode is 1. Check it. Because if r is 1, check this value. If r is 1, then you have 1 minus 1, which is what? 0. Isn't it? R minus 1 is 0. 0 multiplied q is 0. So you have 0 divided by p. 0 divided by p is what? 0 plus r. R is 1, so it's get 1. Are you guys with me?
Yes, Doc.
Yeah.
I'm just trying to break this one down to 1 for you. Okay. So that is it. So again, we'll find the mean and the standard deviation. Emily says, will you be given? Yes, all of this will be given to you. But you can now see that many will be given to you, so you should know them. Okay. So let's look at how negative binomial distribution looks like. It's right skewed. Let me ask you something. If you draw this, okay, and then you draw this, which one is right skewed? The top one or the down one?
The down one.
The top one.
Mankasa Mumbeti. Okay. But I know, papa. Right skewed. How does it look like? One of you is correct. But Emily, the fact that you are smiling means that you are not correct.
Yes, but I'm looking at it from my right.
Yeah. Always look at the skew as a flat point. So if this is a flat point here, this is left skewed.
No, okay.
If this is a flat point here, this is a right skewed. That's how the skew this is done. So this top one is a left tail, and this one is a right tail. It's not where the thing is peaked. No, it's rather where the thing is flattened. I think you got it now.
Yes.
Okay. So let me just delete. So that's the first characteristic. Second, as the R increases, okay, the whole distribution, the negative binomial distribution becomes more symmetric. That means we are moving towards normality. Now, do you all remember what the R here is? Do you remember what the R here is? We've been using it all this while. Are you here?
Yes, Doc. I think R should be
the number of successes.
Yeah.
The number of successes that you want to achieve before in this case, before the experiment will stop. The number of successes.
Yes.
What is a yes?
Sorry, that's the number of successes. Yes.
Yeah. So, I mean, put it down, because sometimes we'll be talking about R, and if you don't take care, you have actually not using it. Okay. Now, larger tail means that the longer tail is going to happen. Over dispersion means that the variance is bigger than the mean. Unlike the Poisson, okay, we'll look at the Poisson next time. Unlike the Poisson, where the mean is also the same as the variance, the negative binomial distribution allows the variance to be bigger than the mean. But in a Poisson, they are the same. Okay, they are the same. But here, the variance is bigger. And you can understand why the variance is bigger. Okay, that tells you the high variability in this case. All right, let's take a typical simple example. A basketball player needs a shot. He just needs to throw the ball into the basket, a shot, with a probability of 40%. If we let X be the number of shots until she makes her third basket, okay, her third basket means that R is 3. That's a number of success. If we what is the negative binomial distribution? Why is this a negative binomial distribution? And then find the probability that X is 7. So first, why is this a negative binomial distribution? What makes this a negative binomial distribution? You can tell us. First thing, look at it carefully. Each basketball shot is what? Each shot. Watch it. It says a basketball player succeeds a shot with a probability of 40%. So a shot is what? It's a success. As long as it has a probability of 40%. So a shot is a success with a probability of 40%. Now, how do you know that the trials are independent? This is negative binomial distribution. They must be independent. Because the way the first shot is done doesn't influence the way the second shot is done. So that's the second one. So first is that the shot is a success with a certain probability. Second, the trials don't depend on each other. And what can you say about the probability itself? The probability, will it change or it won't change? Will it change or it won't change?
It won't change because the shot is independent.
Sorry?
So it won't change.
Yeah. So the probability doesn't change. Okay. The probability doesn't change. Now, if you look at it, it says that the X is the number of shots until the third basket. And we are told that the third basket means that your R is 3. So what does that mean? It means that X.
Now can I try?
Yeah.
Okay, so it means it can't be geometric because the success is more than 1.
Yeah, that's 1. Now, let me ask you, the third success, does it occur on the trial K? Yes. The third success occurs on the trial K. Okay. And so K can be said to be a success. I mean, I just hope that you understand, because X is equal to K. So if, I mean, X is equal to small x, or S is equal to K. So all of this gives it that nature of what? Negative binomial distribution, or negative binomial random variable. Okay. So those are some of the points that gives it a negative binomial distribution. Now, the reason why I ask this question is normally the books don't do that. But the reason why I keep asking this question is I wanted to know what distribution you are dealing with before you attack it. Okay, so now let's find the probability that S is equal to 7. We know the formula, okay, unless you didn't have it. But the formula was given as, let me just remind you. Let's just go back here. This was the formula up here. X plus R minus 1, and then R minus 1. Okay, that is a combination. And then P raised to the power R, Q raised to the power X. And now, in our case, X is what? 7. Okay. So if X is 7, how will you work that? So you're going to have X to be 7, right? So the top part, let me just put it here. Okay. So let me give you the formula first of all. So in this case, capital X is going to be what?
7.
And then 3 is going to be what?
R is going to be 3.
3 is going to be what? R is going to be. All right. So minus 1. So what will be the top part of the bracket?
9,
So that
2.
would be 9.
No.
9,
Yes,
2.
together. All together.
So into bracket, the combination of 9, 2, then we have 0.4 raised to the power 3.
Oh, will it be 9, 2?
And then
X
that
is
is 7 plus 3 minus 1.
9. Yeah. And 3 minus 1 is 2.
Oh, would that be? Oh, no. Then I think I've made a typo. Oh, sorry. No, that's not the formula you use. Okay. This formula, watch it, is failure. I've been written up there. It's a formula for the success. Yeah. So note the formula for the failure and the formula for the success. Because sometimes you ask for the formula for the failure. It doesn't mean they will use the word failure, but you will know the formula for the failure. So now, if you are to use the formula for the success, because let's go back here. It says a find probability of X equals to 7. That is success. Why do we know that? Because you were told that the probability you were given was not probability of failure. In fact, I don't even think you ever be given probability of failure. You are rather given probability of success. You deduce the probability of failure from it. Okay. So in this question, the basketball player succeeds. So that's why you have the probability of failure. So use the probability of failure formula. Please write it down as well. Okay, so now you substitute and let me know. So the top part is going to be what?
Like 9, 2.
No. You are using this new one. But please know that this new one, K is X actually.
So it will be 6, 2.
Good. Do you all agree?
Yes.
Yeah. To be 6, 2. So combination wise, what would that give you? 6, 2.
This combination 2 is
you know the 2 will lead the numerator, because the combination is 6 factorial divided by 2 factorial here, and then multiply by 6 minus 2 all factorial. You know that.
360. Let me get 360.
Sorry, I'm not going to type. I was
You're going
writing
for
it
both the 6 and 2.
in.
You won't
Okay.
get that. You won't get that answer you get.
Okay.
Check it again.
To other critical staff within the
15.
Exactly. That's the right answer. 15. So when you do that, you're going to get a value of 15. What about the next one? The next one is going to be what? This PR is going to be what? We're giving the probability of success to be what?
0.4.
0.4.
So it's been 0.4 raised to the power
3.
3. And then you have 0.7 raised to the power
6. No, Doc, 0.6.
Sorry,
Raised to
0.6
the power
raised to
4.
the power 4.
4.
Yeah, 4 will be 7 minus 3. So when you do that, this is the first one. So 0.4 raised to the power 3, this raised to the power 4, that will give you a value of
I think 0.02456. Okay.
So you're going to get the first one to be 0.064 and then 0.1296. You multiply all of that by the 15, which is a combination you had. And that'll give you 12.44%. What does this mean? Well, this was it's just to find the probability of success. The probability that if I pick, a shot, okay, that particular shot is going to be 7. 7. The success first shot is going to be 7 times. In other words, the number of times before this girl will throw the ball into the basket is going to be 7. So this one, I gave you the value. So it becomes...
But please, is it the number of times she will throw the ball in the basket, like the third time he will throw the basket?
The number of times until she makes her
3 shots.
Her 3 shots.
Okay.
Successful one. Successful shot. Oh.
Yes, Doc.
Yeah, successful shot. All right. Let's look at the mean, because it says that you should find the mean as well. Okay, find the expected value of x, find the variance of x, find the standard deviation of x. Okay, so let's start with the expected value. We know the formula for the expected value here. This is it. So this would be what by what?
Would be 3 over 0.4.
So, Doc, 3 over 0.4.
Good. That'll give you what? 7.5.
7.5.
That's it. So that's the mean. Now take note of that mean. Let's find the variance because I'll come back to it. Let's find the variance. The variance is going to be something like this. Let's not delay much on that. Okay, you substitute, once you know the formula, you substitute, you're going to get 11.25. Okay, and then the standard deviation will be the square root of that variance, which will be that. Okay, now I think this is going to be a test today. Oh, you don't want to test? Sorry? Actually, this is the last one.
That's the assignment.
Yes.
Please, Doc, assignment.
Okay. You got to take a screenshot of this. If I give it to you as an assignment, you're supposed to give it to me Friday.
Okay.
No, don't do it as an assignment. Because the thing is that you are going to copy. Get a point. I know it. The way Albert has been smiling. All right. So do this one and submit it. And then next time we meet, we look at Poisson distribution. And then normal distribution. Okay, and then that will end the distribution part. We'll then proceed to other ones.